Hi everyone, I'm James Maynard. I'm a professor here at the Mathematical Institute in Oxford and I work in analytic number theory.
Hey, my name is Lasse Grimmelt and I have the pleasure of being a postdoc here working in the number theory group with James.
So today I want to talk about the progress that we had with Jared on the Fourier case and on considering two different congruences. So that was in the last two weeks ago now.
So this is with the two different congruences is with the uniformity in the second.
In the second congruence, yes. And then we quickly thought about how our method plays into your amplification setup with the additional congruence. And then last, if there's time, still what I'm doing with Yuri now.
Okay.
So let's start with the Fourier setup. So in the Fourier case setup, let's remember that we wanted to parameterize a double coset of matrices. Let's say with n1 and 2 d, where we looked at G of the form q1 s2 q2 s1 with, let's say, it's a matrix with determinant d, and we had like some congruence conditions n1 divided as 2 and 2 divided as 1. So the main thing I want to talk about here today is that now we feel we have definitely a nicer way of thinking about it, which also should make clear that from the setup, like these GCDs and possible things don't really matter, and how this nicely fits into our new black box. So this is before the Cauchy-Schwarz. Now you do an additional Cauchy-Schwarz. So the set that you're really interested in is somehow you have pairs G prime, where, like, let's say one of them is in n1 and 2 d, and the second coordinate is in n1 prime and 2 prime d prime, where the left columns are the same. So we have like q1 is q1 prime and q2 is q2 prime. Yes. So we Cauchy-Schwarz so that the q variables are kept on the outside. So we get twice the determinant conditions and we have the left set the same. And we have the divisibility condition. In application, D is like something like a n1 minus n2. But since we don't have, like, morally we just look at all the n's are fixed on the outside. Yes.
Yeah, okay, that's just the thing I was going to check. So D depends in some way on n1 and n2.
Yes.
Because obviously it's multiple of the GCD. But,
yes.
Yeah.
Yes, and after this Cauchy-Schwarz, as long as we assume Selbach eigenvalue, it doesn't matter that they are all fixed on the outside, and it's just a fixed quadruplet of all the n's and all the d's which belong to that. And then, like in our black box of how we write it now, at the moment, the best is now to forget the divisibility condition as a set condition, but write it as an indicator function, because our black box at the moment says completely, okay, we should think about it not as that we look at certain sets, but we look ahead the ambient space and have an indicator function which we are interested in, and our method works as long as the indicator function is invariant under the right group action. So what does this mean in this case? In this case, this means we are looking somehow at a weight on G and G prime, where this is the property that this pair is in these congruence conditions. So in other words, it's like something like 1. Oh, let's swap to blue. Oops. Like 1 n1 divides as 2, 1 and 2 divides as 1, and then 1 n prime divides as 2 prime, and 1 prime, I guess. 1 and 2 prime divides as 1 prime. So I think, so we talked about this already before. My main point is now that we finally made all the parameterization explicit, and after we realized that the next step of the parameterization is not really a property of the congruence condition, but it's a property of the ambient space, then it becomes clear that no coprimality conditions can destroy our parameterization. So the setup of the method surely works also in what makes the case break. So that's the nice thing that I wanted to mention here, that after we understood this correctly, we can be at least sure that the method, the application of the method, can't run into the same problem as the BFI approach does, because it doesn't really care about the indicator function. Let me be a little bit more precise with that. So
just to re-paraphrase what you said to check that I'm understanding correctly, you're saying that in your specific situation you have this alpha n that has these different divisibility conditions, but any alpha n that satisfies a few simple group transformation properties
can be counted modulo input. Yeah. If we call this this complicated set, let's say we call it with a vector n and the vector d, where this is all 4 and d is the 2 d's, and then this is in reality equal to, if we want to sum over it, then we can look at those pairs g prime, which are in the support of this function, and then we can ignore the divisibility condition here. So the ambient space, the space that we parameterize, doesn't really care about the divisibility conditions. What we care about is then that this indicator function is invariant under the right group action. So we need to find the group action which does that. And in this case, the group action is just, if we take gamma in gamma 2 of like the LCM and 1 and 1 prime and 2, and 2 prime. Where the gamma 2, let's remember that notation we have introduced is the one where the top right entry is divisible by this and the bottom left entry is divisible by that. And then we take integers nu, let's say, which are in n1 prime and 2 prime z. And then we have a group action of pairs, let's say gamma nu acts on g prime. I think maybe red is good. Oh yeah, gamma nu acts on g prime diagonally in the first coordinate. So gamma g, gamma g prime, and then via upper triangular matrix, so n Iwasawa matrix, from the right in the second coordinate, and then if gamma and nu are in those sets, they leave alpha invariant because they preserve the divisibility conditions.
This is with, so, and our G set has the vector D of determinants fixed.
D prime, yes. That fixes the determinant, and here we act with determinant 1, so that doesn't change the determinants in all of these matrices. Then from the right, if we act by an upper triangular matrix, I mean just multiplying it out, you see that shifts, if V is a multiple, it doesn't shift, it doesn't change S1, S2 with the prime variables. And from the left, we on the top right, the 1 variables are preserved, and on the bottom left, the 2 variables are preserved, so it fixes the divisibility conditions.
And the divisibility GCDs between the sort of N1 and N2 type variables are handled in the V nu action?
No. The bad GCDs in BFI were cross GCDs of N1 and N2 prime, and they are not here.
Yeah, in the gamma.
They are in here. So, and that is exactly why their approach didn't work, because here these cross GCDs appear in both places, but the way they try to do it, you don't see this effect here. But this group acts on this, and our black box doesn't care. Like the way we have written the main result, it doesn't care about any common divisors between this. And after we have translated it to the group, the structure of the alpha and the divisibilities is completely disappeared, because now the black box just says, given a matrix space, and a subgroup which acts on the space and leaves your alpha function invariant, this is the result we get, and this is the counting result we get. And yeah, this is a very, like, in our proof, we never, at no point in the proof we need that those two arguments are co-prime, so this is just how it works, and this is just what it gives. And like when we did it, when Jared was still here, when we tried it, then we always carried around the divisibility conditions everywhere, and it's just unnecessary information. If you realize this in the first step, then it comes down to, oh yeah, now it's about getting a system of representative for this space acted on by this double space.
And all, like, so the answer will depend very slightly on these GCDs, but the key point is that this is all encoded by the group, which is...
Yeah, the answer will depend. There is slightly, as like in our black box, and I will come to that later. In our black box, you remember there's the R part and the K part. And in the K part, you still need to supply some information about what your set does. And there it's not trivial to see. This we have realized, so the GCDs are not really the problem, but in what we have worked on previously, let me tell you, let me later. So there we did also. So we with Jared together, we wrote all of this up, and at least now we have finally made rigorous the application of the whole method. Like we have said, okay, this is the counting problem, counting, and then this gives like a main term. And we get an error term, which is like r to the 1/2, k to the 1/2, and we have this we can handle clearly, and this we have written down in explicit terms and we can do, but this we still need to do a little bit. So there's still something to do, and I will explain to this in the next step. Good, so that's the first thing we did. So here I think I didn't have any questions for you. That was just like that we worked on that. Then the next thing is we wrote down a first heuristics what we expect with two different congruence classes. Let me write down precisely what I mean by that. And that I think becomes quite interesting if it compiles. Yes. So what we looked at is what they call, let me remember, special case 2 was the case in which the Q variables are already 1, right? I always need to remember the BFI, the cases. Oh yeah, okay. So we look at the type 1 term some case, just as a prototypical case in which we don't need to do another Cauchy-Schwarz and want to build an extra variable. So in the dispersion setup, like let's say we have a new congruence variable v, eta v, and then we sum over q of size q, r of size r. So let me first write it in as a general sum. M of size m, n of size n, alpha m, beta n. And then, so now we do like mn is congruent to a mod qr, so that's the standard one. And then we put in mn is congruent to b, and b is allowed to depend on v and even on r. I mean, of course, we keep it outside. They should be symmetrical. Mod v. Yes, and we subtract like 1 over by q v r. And there are some coprimality conditions which I am not writing. And then, like, just because it's the easiest to write, but I mean, from the method, it's somewhat clear that it doesn't really matter if we do an extra Cauchy-Schwarz. So if we can do it nicely in the case, what they call special case 2, where alpha m is just 1, then it's clear that after Cauchy-Schwarzing there's still something possible, and we did run the heuristics. Then we got, then let me do how we do this. So we write it as Mn. I think we never talked, I think last time we talked about it, it was unclear whether you believe that this can be put in dependent on V and R. Do you still remember what the last was what we talked about?
I think last time you claimed, provided you had some suitably small capital V, you can make B V you can let B depend on V at least and make it totally uniform.
Yes.
And I think you said that this was because in your setup, all the uniformity type issues got pushed onto starting points, and then you just needed to deal with some separation properties at the starting points.
Yes.
But I think you never
explained it, right? Yes, exactly. And let me swap what I want to do. I want to do gamma q is equal to 1. I think that's the more easy case. Let me give 1 second. So we want to do gamma q equal to 1. So we always want to do, So we start with this system of congruences. I need to just remember the right thing we had here. Yes.
So hang on. Your overall claim is for gamma q being 1, right? You're only, or are you trying?
No. So my overall claim is that in every BFI case we can put in such a variable with different strengths, and morally it works the same in every way, because in the case of a type 2 sum, I do one Cauchy-Schwarz, exactly how they do it, and then if gamma q is 1, I don't need to do another Cauchy-Schwarz, and it's easier to see. But if I need to do more Cauchy-Schwarzes, it still works morally the same way.
Okay, fine.
So my claim is it works always. In this case, it's the most easy to put it in and to see what the dependence is. Yes. So let me think about this. So if we do the normal dispersion method setup, yes, let me do this now slightly, not too fast. So I'm proposing we get the following system of equations, and let's assume we put the n's on the outside and have. This is definitely not a necessary conditions, but I think it just makes it a little bit easier if we have no common divisors. Then I'm saying we have the following system of congruence. We have the following system which captures this. Let me see. So we have Q1, N1, Q2, N1, S2 minus Q1, N2, S1 is equal to A N1 minus N2 over R. Then we have N1 T2 minus N2 T1 is equal to B nu, or let's keep it just as a B variable, and we know it may depend on some other things. N1 minus N2 over V. Yeah, let me think about this. So and then we have RQ1 S1 minus V, T1 is B, V minus A, and we have that N1 is congruent to N2 mod RV. Let me think about this for a second. So I'm claiming that if I start with these equations and then do the normal dispersion Cauchy-Schwarz, where I now keep the m variable, I don't double, I keep it on the inside of the Cauchy-Schwarz, and I keep the v variable on the inside, which one may, on the outside, so V behaves similar like R, that's why we get a congruence on both of them. Then I'm claiming this is the system of equation, and we wrote down the proof here. Does it seem realistic to you? So if V is not there, then yeah, is that believable?
Yeah, something like that looks right. Yeah, certainly if B just depends on V, then I guess you could just put all variables in congruence classes mod V from the outset and then go through the entire PFI work.
Exactly.
And you should get essentially exactly what you had before, but you're losing powers of V.
And you lose a lot of powers of V.
Yeah, but that, at least as a proof of concept, should say that provided you're an epsilon away from the cases, you can handle V being some small power.
Exactly.
So I totally believe that you should be able to do something, in principle, fairly uniform. So I guess the question then is just, that's a very inefficient way of doing it because you're losing a factor of V to the 10 or something like
that.
And
I'm saying we lose a V to the 3 or so.
Yeah, sure.
Okay. Let me write one more time here, like we combine those, and like if we call this one here D1, then what we end up is like with a Q2 and 1, just to see then why, like in the justification of why we lose what we lose. S1 is minus D1, and we have like N1 congruent to N2 mod RV, and then we have RQ1 S1 and 2. I mean, it's of course a bit technical everything, but let me just bring it to this point, and then so we make some t variable implicit, and then this is what we end up. And importantly, like if we now look at we have here the system of congruences. So if we are in the special case gamma q is equal to 1, then the q's and the s's exactly run here over an SL2 system where we have two congruences. And so if the n's are on the outside, then this doesn't matter and we can sum efficiently over it. We get, of course, then the n over r, n larger than r condition in BFI becomes now slightly more restrictive, but theoretically one can also keep the v on the inside, so this should not be really the limiting factor. And so this is the normal BFI case, and we have now this additional congruence condition, which is exactly like that in the matrix. We are looking at the Q1 S1 term, so let's say the A, okay, maybe I don't use A, so we have Q1 S1, and now in this matrix it says exactly that the product of the diagonal entries is in a certain fixed congruence mod V, so we know that if the group before was gamma 2 N1 N2, then now to fix this congruence condition we need to increase the level of the group by a factor of V, and since this now fixes V squared many points, we get V starting points to get the right congruence again. So we get this plus V many starting points, or like starting points. And then the moral is that these starting points here should not interact in a bad way with the other group structure, and so we get a square root cancellation in the starting point, and so the loss is from the square root cancellation that we here only get square root cancellation in the starting points, and that the V increase the level size. And yeah, those are the losses we get. And let me write what we get, for example. If everything done here is correctly, then yeah, one second. Yes. So then we say that we get something like RV less than N less than X over R to the 1/3 V. So if V is 1, this is exactly the BFI range for this case. And now we make it here bigger by a V and make it here smaller by a V. So it slightly reduces the N range. And morally, here it seems like that V is 3 times as bad as R. So V, V is 3 times as bad as R. And if you remember, there's the BFI result where they do this with R on the outside and Q on the inside, and then they count the primes.
Yeah.
And then their range is R is less than N to the 1/10. And so if we kick out the R variable and just have a V variable, then the worst we should get is that V can be up to N to the 1/30. So that's roughly the order of magnitude we need to expect, I think, for the V variable. So in general, it behaves like it's definitely worse than any of the variables here, because we lose something in the starting point and we lose it twice in the level. But it's like 2 or 3, a factor. The order of magnitude is by a factor of 2 or 3 worse than the losses in the normal BFI setup. So then you mentioned, and we looked about it shortly. So now the question becomes, is this useful for any applications? And there we were not exactly sure, but we can of course look into the bounded gaps between primes, where I think Yuri checked this, we had, like in the current paper, is 49 variables or so, like you choose a 49-dimensional sieve. So we have and we do a Selbach sieve, so we have Q1 up to Q49, and the prime pair, the corresponding other pairs, I guess. And we can now, if one assumes they are well factorable, which of course they are not, then surely we can probably put a full range in. And of course we would need to check if they are just having if there's no additional factorization property, let's say one of them is very long, that's definitely what we always need, because we need to have that the inner congruence is fixed mod 1, the long one. So if one pair is here very long, then maybe we can break the 1/2 barrier for the product for the other ones slightly. Do you think that is worth to follow and has chance? Is it a reasonable thing to try? Now considering what roughly the sizes are?
Yeah, I think this requirement that you have one super long variable is going to completely kill all of everything that's going on numerically. I think the main term contribution in the Banner gap stream primes thing, and this is a bit approximate because this is sort of when 49 tends to infinity, but I think it's still morally true even when 49 is when you don't have these exceptionally long variables and you have the product of the remaining.
So all of them, I should think of them, all of them, the main contribution is roughly balanced, or what should I morally think about it? Or is the main just not one exceptionally long? Or
Yeah, I think there's multiple scales that are interacting, so it's a slightly subtle thing to do with the precise choice of weights. Morally you're having that. So it's not perfectly balanced. Perfectly balanced with them, you have 98 variables, and so it would all be of size x to the 1/2 divided by 98, so roughly x to the 1/200. And some of them, it's important that some of them are allowed, the biggest one can be a bit bigger than that, but not massively bigger than that. And so it should certainly be the case that the product of any 97 of them is at least has the exponent sort of 99% of what the maximum is, because it highly concentrates on that sort of situation.
Yeah.
So
then I would expect that our current automorphic forms don't help much in that.
Yeah, I think I would be skeptical of any of that sort of thing helping in this sort of situation.
Let me think about this. Yeah. Okay. Okay. It's of course nice that we in any way can do this in a highly non-trivial way. But okay, then this application is probably not. Oh yeah. Okay. Yeah. Okay. It is more information, but I guess that's so. I know. Okay. If you already said the main contribution is from other ranges, then it's like zero information there, I guess.
Yeah, so I would have thought that the numerical benefit that this would give would be so tiny that you wouldn't be able to see it.
Okay, good. Yeah, is there anything else? Like, of course, we have now done this only in this one case, but we are relatively sure that this propagates through the other case. It always has the same influence. Like whatever you do there, you just put in, you carry another congruence with you. And of course you need to be sometimes a bit careful when the ends are glued. Like, okay, it's not completely clear because you glue sometimes variables and so on, but...
Yeah, so when we talked about it before, I was a little bit concerned when you were introducing some of these variables where you have no control over the size of it. When you write it in this form, where you keep all your unknown congruences just as congruences, essentially, and so you don't have variables that could be exponentially large in terms of x, then this completely makes sense. But yeah, I guess the thing that I would have in mind is that in principle, you could have done what I mentioned before, the really dumb thing, or put everything in congruence.
I mean, that's how I do. That's how we do it with Valentin and Juntian. There we also need to have one extra congruence on the outside, and we just, since it only needs to be delta, and there's some power saving in the inside, it doesn't matter how many powers you lose.
So probably it would have been quite easy to get that range at least with the v
to the 100 or so,
v to the 10 or something, and so if there's going to be a situation that benefits from your work that wouldn't have benefited from that previous approach, that requires it to care about the
numerics very precisely.
Numerics and the quantification. But the problem is that the quantification is still slightly on the weak side because you have something like v being less than n to the 1 over 30. And okay, 1 over 30 is a lot better than 1 over 1,000 or... it would mean that you have to care quite a lot on the size of this small uniform component.
Yes. So either if the gap was exactly at 0, then the old method worked already, and if the gap was not 0, then it's improbable that a 30s is enough or so.
That's what I would have guessed. Yeah.
Okay. So it's still worth it to write up because it's nice to have non-trivial handling of that. But it's not like opening new applications immediately. Yeah.
At least not that I'm aware of off the top of my head. Again, from my point of view, the main sort of thing of interest is the way that you can kind of build a certain level of uniformity into some of the spectral methods. Because if you're not careful, the spectral methods have at least a congruence condition, size of the congruence residue class, the little o1 type factor, whereas at least here you're able to slightly sidestep that by putting all the uniformity into your starting point.
Yeah, and we don't do Poisson, and so you don't need to be careful about that. Yes. Okay, good. Okay, do we have anything else? Because else I wanted to go to a point where we're having a very good improvement here. Okay, let me say what I want to say. So the next thing we looked at, I forgot unfortunately some of the details, but I can still morally say to you what it's about, is how this plays together with the amplification method that you use there, and in particular how this plays together with the case which is missing to break the 1/2 barrier of the 4, because I will write things which are surely wrong because I forgot exactly the right setup, but we at some point if you write the amplification method setup, then let's say here's an S variable, and this is like one, there's a Cauchy-Schwarz, and everything is complicated. But if you write the amplification setup, you essentially have somewhere an additional congruence condition which looks like N3 is congruent N2 mod C. Okay, this is not exactly, but somewhere there's an additional congruence, which then in your paper, you handle essentially trivially and lose a C to the 10, or like by putting everything into congruence classes. Now, this congruence condition is actually much better than the congruence condition we looked at in the additional congruence, like if n1 times n3, because this one is now fixed by gamma naught C, I guess, because this fixes n3, assuming coprimality, because gamma naught 3 fixes n3 over n2. That means that we don't need that we sum over all the starting points, but all the starting points are already in the problem, and we have a group which fixes the congruence condition. So essentially, the amplification setup translates in this method to the best possible thing you can happen. Like you have all the starting points, so you get you hope to get square root cancellation, and your group is not too, like we don't need to have more starting points than necessary. So in the language we had there, that means the loss is maybe no longer it's not like 3 times as bad as the other losses, but maybe 2 times or maybe even 1.5. Like it's getting close. And if the loss here becomes extremely good, one could do the quadruple divisor function by just amplifying very much. And we think this is not possible with this, but it's much closer. We are like over half of the way of the range of C there, which you would need to choose C to amplify yourself around the quadruple divisor function. Probably there's a very good reason why this can't in any case do this, but we still found it interesting that it reaches definitely closer to that. Unfortunately, we did this 2 weeks ago and I didn't have my notes, so I can't give you exactly the details, but I think from it should be clear that in such matrix setups we can handle the C quite good, but my guess is that any loss in C makes the application impossible and we can't hope to have no loss, but yeah, it's still interesting that you can do better than before in that. Do you think there are other cases where one needs the amplification method, like with not C to the delta, but where again like C to the 1 over where like C of size n to the 1 over 10 is interesting, because I think like something like C is of size n to the quarter suddenly would open something like the quadruple divisor function, and I think maybe we can get to 1 over, I don't know, 6 if we are very optimistic. Are there possibly cases where this is still like opens more applications than n to the delta, or is it again a case where between these two there's not much?
Okay, so a few things. One thing is it would be worthwhile chatting to Alex a little bit, because he had some works that were also, one consequence of some of the things that he did was to treat the sort of C averaging in a less trivial way than I did, and that correspondingly gave triple convolutions in slightly wider ranges.
Did he write? Is this appeared in something that's written up, or is it like something he worked on?
I can't remember.
Okay.
I think it was a sort of side application, and he didn't have any kind of concrete applications. So I think this was connected to work that he's already done, but maybe he just had it as a sort of side comment or something in one of his papers. I think it's related to some of the stuff that's already appeared on the archive. But it's best for you to double check with him, because he certainly didn't write it all up, almost precisely because he was improving a fairly trivial polynomial loss in C to a better polynomial loss, but didn't have a kind of concrete application. Off the top of my head, I correspondingly don't know of any concrete applications where this would have a major effect. I mean, there's lots of variants of these primes in arithmetic progressions type questions that you can ask, where you can have different assumptions in different ranges, and with the sort of de-amplification style argument, suddenly when you're in the sort of small neighborhood of what was previously the critical case, you now have a much better estimate. And this means that that better estimate will have a wider range. And so when it takes over from kind of previous estimates, if you have one, say, quintuple convolution, then there's lots of ways of pairing up variables, and there's a few different methods depending on the size of the different variables, and there's all these different messy overlapping estimates, which are all kind of very numerically quantitative, and in some ranges one will do better than the other, and the better your C dependence, the bigger the range it is to use this different setup. And so there's therefore lots of possibilities that if you kind of come up with the right question or look for the right version of the question in the literature, you might be able to quantitatively improve something. However, I'm not really aware of many situations when this is the absolutely critical range, and therefore I'm not totally sure if you can do anything qualitatively new. I guess one thing to check is the sort of 6 prime factors of size x to 1/6.
All right.
That I sort of feel.
So can I again think about this as a 6 divisor?
Yeah.
Okay. So we have like n1 up to n6 of size, and let's say x to the 1/6, and we want to do this. So this is not known with q larger than 1/2.
Yeah. So I think I believe that sort of I believe that this should be much easier than the 4 factors of size x to 1/4, but certainly in the literature there's nothing that handles this case.
I mean, okay, that's interesting. That's okay. I see a non-zero chance that we can, because that seems to me like something where that seems like the amplification limit is maybe somewhere in between. Of course, I've not thought about 6 factors, how we need to think about all possible arrangements, and so so 6 is more difficult than 5 here.
Yeah.
Because it's even, I guess, and likes to combine to 1/2, and 1/2 is bad.
For example, yeah.
Okay. Oh, that's a good point.
And yeah, I guess related to this also is the ternary divisor function with 3 factors of size x to 1/3, and because in that situation we can handle this beyond x to 1/2, but basically this is always using estimates coming from algebraic geometry, and this
no spectral methods.
And so yeah, for at least the totally balanced case with 3 factors of size x to 1/3, I think no spectral methods know how to handle.
We are allowed to average. We average over Q, right? Or
so the algebraic estimates are able to handle it without the average over Q, but even averaging over Q, I don't know of any automorphic spectral method that can get non-trivial results for D3 of n in general.
For any Q larger than 1/2.
For Q bigger than 1/2.
Oh. Well, that's interesting. Yeah, somehow my gut feeling is that maybe for those cases, if you assume some reasonable conjectures, probably it may be possible, and like the quadruple, I guess even with like my feeling would be it would be very surprising if you can de-amplify your way around that problem, and even if you as long as you don't put unreasonable things like cancellation between different cusp forms in, I guess it just can't work. Whereas here, this seems more reasonable.
So for what it's worth, yeah, skeptical that it will work in any of these situations.
In any of these situations. Okay, good.
But I would be very happy to be proven wrong.
Okay. Okay, that's good. Okay, that's a good point. That's I was not aware. Let's see. I feel we have a lot of possibilities to do so. Let's look at that. Okay. Then, so those were so far the good news. And then there's also a little bit slightly bad news. Namely, let's look again at the whole setup of the method. So, well, I think we are getting there, but there's unfortunately. No, let me just start with the method. So we are running a little bit always. We always need to do things again because we realize that applications require more generality than we had written it up before. Surely, like a lot of the applications I talked to you before, like the divisor function, those are all set, like they surely work with what we do. But our goal is to write the method that it can handle like the two applications, like which are in some sense extremal cases, which we want to look at, is that we look at like an L function estimate, and maybe two are complex conjugated, where we have 4 different characters, which and we are interested in getting an asymptotics and say what range of the moduli is permitted to get an asymptotic formula. And Berke Topaculari has a paper where he considers 2 pairs of characters and gets a result, but he uses Blomer-Milicevic and loses already factors of that, just which he can't prevent because he doesn't use the right spectral approach. And then Kaneko has a paper in which he obtains like a full Motohashi type formula for all characters being the same. But I don't understand that paper, and I'm suspecting I don't know. I don't understand that paper. So that paper, he says he can't improve Berke's result, and I don't understand this statement because I would have thought he should, but I think he probably understands his work better. So I would leave that out and just look at Berke's result.
Hang on. So sorry, the characters are to different moduli.
Yes.
And we're expecting the main term, which is what you'd expect.
Yes.
And then you're going to get some error term, which would be clearly power saving when all the moduli are small, but you're going to have some loss depending on theta and the size of the moduli complexity.
Yes. And we say that our estimate is that in the error term, if like, let's say, if all the QIs are 1 Q, if all of them are the same, then we think we save a full power of Q in the error term over what Berke had. That is our hope. And our hope is also that we can give it for 4 different characters, which I think with Klostermann sums is again possible, but would be so messy that it's essentially hopeless. Whereas for us, it's messy, but it's possible. So that is one of the things we want to do. And then the other thing we want to do is the whole BFI setup, of course, that we talked about all the time. And so why do I mention those cases? Because if we think about the general setup of our method, let me take a look. Right. So we have now generalized a bit, which I'm not sure if at some point we just need to stop trying to generalize, but at the moment I think it's still, if we want to handle all those cases, we still need to do something a little bit more. Namely, we need to look at matrices, and I will ignore some GCD conditions. So let's say these are matrices with determinant hk of integer matrix. Then I have some, let's call these G. I have some weight alpha on G, and I have a weight f on G, where this thing is fixed by a certain congruence subgroup, and this is a smooth weight. And then we want to say that this is main term plus an error term, which is r to the 1/2, k to the 1/2. So what's different to what we talked about last time? Different is now we want to assume that the determinant has two parts. Why do we want to assume this? Because let's say, because the beta h variables should go into the r part and the gamma k variables should go into the k part. Why do they need to do this? So in all Dirichlet-Ibanez applications, beta h is 1 and there's nothing put into the r part. In all these style of applications, so let's say zeta fourth moment applications, you usually want to have gamma k equal to 1 and put everything into the other part. So if
Sorry, and by equals 1, you mean is the indicator function that k equals 1? And
Yes, sorry. Of course, it's not a constant, it just disappears.
Yeah, sure.
Yes. And so if our black box should handle those two extreme cases, we want to write it in a way that the error term, like that you can put it in. And the reason why we think we can handle this thing here, for example, easier than other people, is that we now can allow some of the determinants to go still into the k part if they are ugly with the r part. For example, if the determinant here has a common divisor with the q's, then we don't want to open the machinery of new forms, old forms, or like to see how it interacts here. But we say, okay, those divisor bounded many, we push into the k part because there it does less harm than in the spectral part. And that should be conceptually very nice because we should require less input from the spectral side because, as I said, we only need to consider them as hacker operators when they are co-prime to all levels, and then they just behave nicely and factor out and everything is just beautiful. But we gain the pain of having them in the k part. And that we have now looked for 1 week because they make the k part definitely more ugly. And we probably can't prove the best possible result, let's say the optimal result, but what we can prove is probably good enough for all the applications and gives exactly is like the additional complications we can't handle optimally, but we still hope that how we handle it is in all applications dominated by diagonal contributions or such things. So what do I mean by that?
Just to check,
Yes.
so you have the choice if you're putting things in the k part or the r part.
Yes.
So the advantage of putting it in the k part is that you avoid having to go into new forms and old forms and things.
And we need to do it if we want to do BFI in the same way.
But let's imagine that we're in this kind of context. So I see how that kind of technically sidesteps a technical obstacle, but of course you could go into new forms and things.
But for this, we anyway need to do it.
Yeah.
Okay.
No. So I'm not objecting to the principle. I'm just trying to understand for this context. The main advantage of putting it into the k part is to sidestep technical difficulties that you would encounter in the r part.
Yeah, for which we are not completely sure if they are only technical. Because no one has done it for 4 different non-primitive characters, so we don't know. We don't know. We think. I don't know what to believe. We decided to not look into that
because you feel it's so technical, it's going to be horrendous.
Yes. Yeah. And we don't even know. It could be that there is something happening which loses one effector of. We don't know. Yes. So that's the main advantage. That yes, I think you summarized that correctly.
Okay. Yeah.
The problem is now that, I think, by the way, I think we're soon, maybe 5 minutes, I think we started.
Okay.
Give me 1 second. The problem is now the following. Let's remember. So how did the K part look like? The K part looked previously like we sum over matrices G, A, B, C, D. Then we have our k weight on G, which is like something like absolute value A plus absolute value B times L plus C over L plus D is less than x to the epsilon. And then on the inside here, we were summing over tau 1, tau 2 in essentially the set, what we are looking at, modulo the group, so over a system of representatives. And then we have alpha tau 1, alpha tau 2 bar, where these are exactly the alphas here. So we have a nice weight with these properties, and then we sum over these double cosets. Oh yeah, what is, of course, there's a dependence. Tau 1, G, tau 2 is in the group. So this is a function which we called W of G previously, which somehow measures how these alpha interact with each other. And if you remember one part of where we wanted to get the strongest possible result, we needed to be able to capture sparseness in these alpha uniformly in G, but that we have all worked out. Everything is fine. However, this, what I wrote down here, is only correct if k is equal to 1. And this was nice, because if you look at this equation here, and here these matrices are in SL2Z. And this equation plus the property that the matrices are in SL2Z means essentially either this matrix is an upper triangular or lower triangular matrix, or there are only boundedly many and it doesn't really depend on L. So this was essentially why our method was nice. We started with a complicated counting problem, and then the input you need to give reduces to triangular cases here. And if you insert a k, it doesn't immediately reduce to triangular cases here, and you still have a quite complicated, I don't want to write it down, but you still have a more complicated counting problem, in some sense, because these are no longer in SL2Z, but in SL2Z over K1, K2. Like, their fractions can be involved, and then you can't exclude that there are matrices with B, C not equal to 0, which, yeah, there's something happens. What we are doing now, and, okay, evaluating this object here on the inside for G not upper or lower triangular is a gigantic mess. That you definitely don't want to do, especially if you want to capture cancellation in characters. You definitely don't want to do it. So what we do is we say that, okay, we give a trivial bound for BC pairs where BC is not equal to 0, just by doing Cauchy-Schwarz. Like if you Cauchy-Schwarz the tau 1 and tau 2 variables apart from each other, then it becomes a little bit easier. If you do this, if you Cauchy-Schwarz away, then the contribution of terms where BC is not 0 loses a factor k over the AL2 bound, over the other bound. And we are not yet sure if this factor of k is a permissible loss. Theoretically, one can do much better than this by keeping everything intact and by capturing cancellation. But if we write our main black box in that way, it becomes a very burden of application to get the right bound here, because I think this is a very difficult object to study, and I'm not convinced that for non-upper or lower triangular G's that this object is even much easier than your original counting problem. Like somehow the whole point of the method is to reduce a difficult problem to an easier problem. If here this is still super messy, then you have not won much. And we say, okay, if this k is 1, then we can always make it much easier. If this k is not 1, then, okay, you lose a factor of k, but you don't lose L's. So in most applications, the L's are what matter. And then for those, you can give still efficient bounds for this. And this is a little bit the struggle we have the last 4 or 5 days, because we really long and hard thought about if we can avoid this, or if we were on two ways. The question is there an easier description for this if G is not upper or lower triangular? Or can we avoid this k loss in the Cauchy-Schwarz? And the answer seems to be no for both questions after 5 days, so that's a little bit bad.
Yeah, okay. How does this interact with the L? So if L is much larger than k,
then this loss is harmless.
Then, yeah, this... But also it looks like you don't get non-upper triangular / lower triangular. Okay, I have to interpret what...
Yeah,
all of these
so
variables.
the problem is, if L is larger than k, or L is less than 1 over K, you don't get upper or lower triangulars. I somewhere here you probably also need to scale with K still. And so the answer is if L is very large or very small, you automatically don't get upper or lower triangular matrices. In the middle range, you get them, and trivially they give you this.
When you were working on this problem before, you didn't put your L's into your starting points. You had your L's in the whole spectral method.
Yes.
And that sort of allowed you to push difficulty from the spectral method to the starting points to have it in this setup. And you had a rather messier argument that handled non-trivial large L's.
Oh, that argument never worked.
That never worked?
No. We needed to invert the kernel bound there, and we know what is the answer, but we were A, not able to prove it, and B, even assuming the answer, we still were not able to make the argument work because we were not smart enough. No, I don't know.
Okay.
So we never had a method that made it work. I believe it's something that can be made work, but this is
because I was only just wondering, as a sort of, maybe it's a silly thought experiment, can you kind of make the L parameter here larger than K to ignore all the K things, and then you have to pay a cost over on the spectral side that then gets you back into all the difficulties that you...
But that loss, I think, will be larger than this K. I mean, we can do this...
Even if you could do all of that...
Oh, no, if we could do that correctly, then probably not. I don't want to speculate. Okay, fine. Because somehow what we thought first, if it were true what we thought first, then yes, what you just said. But after a long time of thinking, we actually got to the conclusion that it's probably not true what we thought, and maybe there exists no such kernel with these nice properties. So we are not sure.
Okay, fine.
But so we believe this loss is harmless, and probably in all the applications will lead to not weaker results. But somehow it's still a blemish on this whole setup, because one would expect that the right way of doing it should again only require simpler information. If we don't have simplified the information input here, we have done something wrong on the steps before, we feel.
But yeah, this is quite a lot of terms that you're treating trivially now.
So funnily in the Fourier case, there's exactly our optimal bound result was exactly by a factor n better than what we should get. So and k is n1 minus n2. So we had exactly a wiggle room for this. So we need to still check it, but it may actually be that Dirichlet Evaniets also have this. So we are not even sure if this is worse than Dirichlet Evaniets. Probably not even. We just hoped to get something better in some sense. So,
but yeah, it might be one of... Okay, so there's two possibilities here. One thing is that there's a kind of conservation of difficulty, and you can maybe push the K pane around in... You have lots of choices, but you're going to have to pay a price somewhere. So you could try and push it onto the R factors and then have to deal with it there. You could push it onto the K factors, but then either you're incurring this loss or you're going to have to do something non-trivial for the sort of many terms that are not up or lower triangular. Modulate speculations about your old method, you could maybe push it on the difficulty onto the spectral side of things, but all of these, it sort of feels like you're having to pay a price and pay some pain somewhere. And often when that's the case, this arises for a fairly good reason, and quite often it means that you can't just come up with some neat trick that sidesteps the difficulties.
So this was roughly the conclusion we got, and so for the moment our working assumption is we accept it here, and check what that does in application.
So for sure, the first thing to do is just to see how much this hurts you or doesn't hurt you for your applications, because it's also the case that you don't want to add another 40 pages to your paper, kind of going through some very complicated argument that's maybe handling this in a non-trivial way. That's probably something that it's better to leave to a follow-up paper or something.
Yes. And the point that I'm getting from this is that, at least with our method, you see where the pain is going. Like you still have full control, and you know that theoretically here should be something possible. Whereas doing it with Kuznetsov's formula, it becomes super opaque, like where it's gone. So that's the general gist which I take away from what we are doing, is that we try to give you a black box, but the nice thing is that there are probably a lot of improvement, like doing the inversion formula better, playing around more with the K parts here. But I think at some point we just need to say, okay, we start this, and then let's see what we can do with this later.
I agree. So I think the main advantage of your approach, and I know we've talked about this several times, is that your approach is just fundamentally more transparent, at least from the point of view of certain applications. And so at the end of the day, you're applying a spectral decomposition and you're applying Cauchy-Schwarz, and those are the two things you're doing. And the flexibility that you're talking about here is slightly different ways about applying the Cauchy-Schwarz step. But we know that there's a huge amount of mileage that you can get from those two fundamental inputs. But that's all you're doing, and so somehow anything else that's equivalent to some sort of spectral decomposition and then some sort of Cauchy-Schwarz more or less should be able to do the same things, but maybe in much more obscure and complicated language. And so anything, the Kuznetsov trace formula is essentially just a spectral expansion. You're essentially doing that with your Poincare series. The key benefit is the whole time is not so much that you have this new method that can now do things that absolutely couldn't be done before. It's just that it's much more transparent about the ways in which you can tweak it and where you have to pay a price and where you have to put effort in and where you don't have to put effort in, which allows you to do new things just because you can see how to play with it. And this sort of more complicated tweaking about how you want to balance it between one side or another side feels very much like you've got something that's fairly transparent, but maybe that actual kind of fundamental work, if you're hoping to improve this by working somewhere else, should be coming in some sort of later paper or something.
I guess we only need to make sure that this loss doesn't lose over the schema.
Yeah, exactly.